All right, so let's take a look at the exam results. I'll pass these out at the end of class. I apologize ahead of time for not doing it before, but like I said, I have a student who still has not taken the test. So on the left side here, you'll see a chart of the A's, the B's, the C's, the D's, and the F's for the 3 exams we've taken. So blue is the exam 1, so on exam 1 we had 9 A's, on exam 2 we only had 5, on exam 3 we had 8, and so on and so forth. So you kind of, do you agree that we have kind of stayed pretty consistent throughout the 3 exams? I mean, relatively the same. Our average on the first exam was about an 85. On exam 2 it was an 80, so it had dropped, and then on exam 3 it's right around an 80 again, so not much of a change. And I talked to you all about standard deviation and how I like that number to be small. In the first exam it was a 12, and I was like, whoa, that's really small. I said it's normally around like 18, so we have trended towards what's normal. Okay, we have standard deviation of about 18 points on this exam. And then these are the actual grades. Let me make this a little bigger so you can see it. That didn't work. Get this out of here. So I'm only showing the numerical grades for the scores on exam 3. So this gray kind of bar shows every student's grades. So the highest was 101, the lowest was a 29, and then these 2 are going to be your previous exams. So you can see, it's pretty good to see that a couple of students here didn't do so well in the first 2 exams, have gone up on the 3rd exam. And then right in this group, everyone's kind of stayed about the same on all the exams. And then we've had a couple of fluctuations here on this end. All right? So overall, I'm pleased. I think most of you are in a position, we have 2 more exams. We have an exam 4, and then we have a final. So most of you are in a decent position where you just have to kind of, continue what you're doing and everything's going to be fine. All right? There are a few students I'm concerned about. And I think those students will know who they are. I would encourage you to talk to me to see where you are in the class. I need to check when the last day to drop is. Is it tomorrow? Is it tomorrow? Okay.
When is the semester over?
We have, after this week, we have 2 weeks. So I thought it was the 31st, but it might be. Okay. I think it's Wednesday, the 31st of July. Is our, well, it's right here. I don't know why I'm not looking at it. Yeah, it's 31st of July is our last day. So we take our final exam that day. Yeah, I agree. Okay, any questions or comments or concerns or anything? No? Okay, so like I said, I'll hand those back at the end. Everyone here took the test? Nobody has not? Okay. Do y'all want them now?
Yeah.
Do you want them now? Okay, I'll hand them out now then. I have also updated in Canvas all the grades for quizzes. There was a quiz, I think, at the beginning. Then there was an attendance quiz. There was the quiz with the quadratic equations that I asked you to go solve from the homework and bring. I counted that twice. So that was a credit grade. If you did it, I looked to make sure you had attempted all the problems, had worked out the problems, you got hundreds. So your grades do reflect those quiz grades also. And I have not dropped any of those yet. I will probably drop at least 1 quiz grade. So, all right, let me just call you out here. Is this Jared? Jared? Paris? Brianna Garza. Brianna Pavon. Here, Marcus. Victor. So the way you can figure out your grade is just you add up the points I took off and take it out of 100, Victor. And then remember, if you did not use a cheat sheet, I added 3 points. And if you did, I took away 15? No, 7. That's what. So the grade, no. The grade online will reflect that. So if you add it up and it says you had 20 points taken off, then you would get an 80, right? But if you didn't use a cheat sheet, you would get an 83. Yes? This makes sense? Okay. Miranda. Gabriella. Here we go. Good catch. Gabriella. Gloria. Albert. Okay. Aaron. Is that Aaron? Yeah. Christian Rodriguez. Nivini. Alicia. Tanisha. Oh, they're right there. Okay. Wait, hold on. Do I have 2? Alyssa or Anissa? Alyssa, okay. And Anissa. David. Davis. Elizabeth. And Mr. Bryant. Steve. Timothy. And James. There you are, sir. I have the original test. If you want a copy of it, I can get it to you.
Oh, no.
Okay, that's all right. Okay. All right, did I miss anyone? Excuse me, sir?
Do you want my second test? So you can put it in?
No, I'm going to put it right here and see how that goes. Yeah, I don't think I'll need it. I can remember that. All right. Timothy, right? No? Yeah? How you feeling? Did you go to the doctor?
No.
You still dizzy?
Not really.
No? Okay.
Yesterday.
Okay. Okay, so while you're getting that situated and looking at your test, I'm going to get us ready to start the next topic, all right? Where the heck is it? Okay, so what we're going to do here is start something called polynomial functions. And just a little bit of history here. You know the packet that you've been working out of this whole semester, right?
Yeah.
That packet was the whole idea behind that packet was most students that take this class don't need any more math classes, right? This is the end of the road for math. So why have you go buy a textbook that's going to cost you $80 to $100? Instead, let's make a packet and cost you 15, 20 bucks, whatever it is, and get you through, right? So the packet has been, it was created originally and then it's been edited for the past 4 or 5 years. And how do I say this nicely? It doesn't do a very good job of a lot of the topics, and polynomial functions in particular, it does not do a good job of. So I'm not even going to look at the packet, all right? I don't want you to look at the packet for this. The homework that you're going to get for this, I'm going to put on the board at the end of class, all right? And those are the homework problems you're going to do, all right? So polynomial functions, in order to start talking about these, I want to just quickly review the functions that we should know how to graph at this point, all right? We know how to graph a linear function. And linear functions look like this. F of x equals mx plus b. We've already talked about this, right? This is like y equals mx plus b. This is a line. We can graph lines all day long, hopefully, right? Someone gives you some linear function, you should be able to plot the y-intercept slope and all that and draw, right? So linear functions are pretty straightforward for us. Then after that, we started talking about these quadratic functions, and that's what the last test was about, right? A lot of the test was quadratic functions, and those look like this. F of x equals ax squared plus bx plus c. And I think next to each of these, I'll give you a specific example. So like for this one, a specific example would be something like f of x equals negative 3x plus 1. And then for this one, f of x equals negative 2x squared plus 4x minus 7, something like that. So if you're asked to graph this, you would do it a certain way, right? You'd use certain method to graph this. To graph this, well, we realize that's a set of steps, right? We have to go through kind of a procedure to do this. This one would open down. We have to find the vertex. We have to find the x-intercepts if they exist. Y-intercept, draw it, right? That was number 10 on the test. No, number 9, all right? So linear functions, quadratic functions. What were these useful for? Linear functions are good at modeling, like people make a certain amount of money per hour. You can model their pay. Anything that changes at a constant rate, you can use a linear function for. Quadratics, I tried to convince you that they're valuable, you know, parabolas and objects on Earth falling, throwing things through the air, right? All that. I tried to convince you that they're important. And now we move on to the next category of functions, which are called polynomial functions, all right? So I'm going to start by writing out what they look like in terms of, like, this is what a linear function looks like, right? This is what a quadratic function looks like. So what does a polynomial function look like? And you're going to hate this. You ready? It looks like this. F of x equals there's a little subscript here, sub n, x to the n plus a subscript n minus 1, x to the n minus 1, plus a sub n minus 2, x to the n minus 2, plus dot, 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 a sub 1, x plus a sub 0. Isn't that pretty? Isn't that pretty? Yeah, so it's not super important that you copy this down and memorize it. I just want us to understand what's happening here, what this is. So I'm going to give you a specific example underneath this one, all right? Just like I did with this. So here's a specific example of a polynomial function. Maybe something like 3x to the 5th minus 4x to the 4th plus 3x squared minus x plus 7. All right? That's an example of a polynomial function. So what you need to notice about this is that it's a lot like the quadratic in the sense that you've got a bunch of x terms in there. Do you all see that? You got some x's. This one had an x squared, and then it had just an x to the first power, and then there was no x here, right? So what was the highest power of x in a quadratic? What was the highest power of x in a quadratic? 2, right? This squared, that was the highest power. What's the highest power of a linear function? X to the, this is a 1 here, right? Even though we don't write it, so the highest power is a 1, right? For the polynomial function over here, what is the highest power you see here? 5, right? 5. But in general, a polynomial function, the highest power you have can be any number. So like this could have been 3x to the 10th power. This could have been 3x to the 256th power. It doesn't matter what that number is. So this number right here, n, that n is what we call the degree of the polynomial. It's the highest power of x that you see, all right? So this is the degree of the polynomial. Now, what do you think all of these things are out in front? Numbers, right? Because just like here, what was the A? It was a number, right? What was the B? A number, right? What was the C? A number, right? So here, this A sub n, A subscripted n, is the 3, right? Here, what's the A sub n minus 1? For us here, it would be the negative 4, right? So all this is saying you have some number in front of x to a power plus some number in front of x to a power that's less than this one, right? And then some number in front of x to a power that's less than that one and that one, right? So it's like the powers are coming down. Do y'all see this? So I went from x to the 5th to the 4th to, oh wait, I'm missing the 3rd. Is that a problem? Well, I actually do have it. It is there, but it's kind of hidden. There is in here, you can't see it, a 0x to the 3rd. Now don't freak out. We had this before. Remember when we had a quadratic and we said sometimes you could have the x's missing? Same thing here. If this x wasn't here, then we would say that's like 0x. Does that kind of make sense? You don't look happy. You don't look happy. Okay. So the main thing that I want you to take away from this is when you look at a polynomial, like what classifies a polynomial is you have a bunch of terms, right, with x's to powers. And you'll have some highest power there, all right? The highest power you see is called the degree. The other thing that's going to be important to us is the number in front of the highest power. This number right here, not these numbers, but that number right there, we call this our leading coefficient. And you'll see how we're going to use that in a minute. So I have a question, and man, I forgot my coffee. Damn it. It's down in my office. I have a question. I'm not sure how you'll do with this. I think someone here can get it. So with a quadratic, I used a in front of x squared, then we use b in front of x, and then we use c in front of this, right? And then for a linear, I used m in front of x and then b. So why not when we're doing this, why did mathematicians use these stupid subscripts down here? Why not just do like a polynomial is f of x equals a x to the n plus b x to the n minus 1 plus c x to the n minus 2 plus y. Why go through this process of confusing everyone by using a sub n minus 1, a sub n minus 2? Can anyone figure out why we go to this instead of this? So what I'm saying is like this would be a sub 5. It's the number that's in front of x to the 5th power, right? This right here would be a sub 4 because it is the number in front of x to the 4th power, right? Why not just call this thing a, b, c, d? Why confuse everyone? Yes?
Is it because the numbers can keep going on but we don't have any more letters?
Exactly. Good. So what if your polynomial has a degree of 100, right? Then you can't do A, B, C, D, E, because you're going to run out of letters, right? You only have 26 letters in your alphabet, and you're already using X, so now you have 25 letters, right? Does that make sense? Mm-hmm. So it's only because a polynomial does not have a limit on how high this degree can go that there's no way to write it generally so that you don't run out of letters. So what we do instead is we use a subscript because, you know, if I did a polynomial that looked like this, f of x equals, let's say, 3x to the 100th power plus 9x to the 99 plus, and I keep doing this, right? Then this right here, I'm going to call that a sub what? A subscripted what? 100, right? That is basically saying that is the number that's in front of the x to the 100th power. And then the next one, this right here, would be a sub 99, a sub 98, a sub 97. And you'll never run out of letters that way. Yes?
Here we say it's going to be the subscript has to be like a n minus 1.
So this is 1 less than that one, right? That's what this is saying. And this power is 1 less than that one. So see, this is a sub 100 because that's the 100th power, right? What's 1? Take 1 away from this. 99. So this one is a sub 99 x to the 99. What would the next one be?
Okay, so
2 less than that, right?
are we saying that on polynomial functions, the sequence of the numbers have to be exactly like 1 minus the 1 plus 1?
No, the number itself can be anything. What we call it, though, is always going to be, it's like we're going to call this number 3 a sub 100.
Yeah, because now we are in the decreasing sequence, right?
Yeah, it's decreasing.
Of 3x to the power 5 minus 4x to the power 4. But can it be other way around, like 3x to the power 5 minus 4x to the power, let's say, 2?
2 without a 4 in here?
Uh-huh.
Yeah. Okay, so let me do
We
that.
call that polynomial function.
Oh yeah, absolutely.
You know, does it have to necessarily be, you know?
The only requirements for a polynomial function, and I really don't want to get too far into this because,
And one more question.
Yeah.
And okay, we say it has to be the power, like the degree has to be
the highest power.
the highest power.
Okay.
Which means if it is 2, it's gonna be quadratic.
Okay, let me get to that. Because you're already seeing that, right?
Yeah.
If the highest power is 2, we're looking at a quadratic, aren't we?
So it's not polynomial function, right?
Well, what we're saying then is that every quadratic is a polynomial,
Oh,
okay?
Now I'm getting
And every line is a polynomial,
Yep, that's what I
okay? So quadratics and lines actually belong to a bigger family of functions called polynomials, all right? Yeah, so I'm not quite there yet. I was going to get there. Okay, so tell me what you want me to write down. You said like if we had that and then
5, right?
Okay.
Let's say plus maybe 5x 2 and then just 3x.
okay, plus
2x.
2x. Okay, so let me ask you first, what's the degree of this polynomial? 5, okay? The degree is 5 because the highest power is 5, right? What is the leading coefficient of this polynomial? 3, because it's the number in front of that, okay? Those are going to be the most important things we need to know, okay? But I'm going to now address a couple of things. Since the degree here is 5, n is equal to 5, that's our degree. That means that we should have a sub 5, a sub 4, a sub 3, a sub 2, and a sub 1, and a sub 0. We should have numbers in front of all the powers of x all the way down from 5, 4, 3, 2, 1, all the way down to nothing. So what is a sub 5 here? What is the number that's in front of the 5th power of x? 3. Okay, what's the number in front of the 4th power of x?
0.
There is none. 0. The 3rd power of x? 0. 2nd power? 5. And then 1st power of x? 2. And then what about the number that's by itself at the end without any x's? There is none, right? So this would be 0. You know, had we put like plus 1 here, then that would be 1. Understand? Okay. Does that make a little more sense, writing it this way?
Yeah.
Okay. So let me erase a lot of this and let me kind of recap the most important aspects of this. So looking at this right here, this general polynomial, n is called the degree, right? N is the degree, n is the degree of the polynomial. And remember, that's the highest power of x that you see, all right? And then a sub n is the leading coefficient. And that is the number in front of highest power of x. All right. And we have a couple of conditions here, all right? That, well, you know what, I'm not going to get into it. I'm just going to leave it like this. I'm just going to confuse you. Yes?
So the degree is the leading coefficient.
Mm-hmm.
So we put the numbers, or what would be the numbers before factoring or after?
It's the number before you would do any factoring. If you're going to do factoring, it would be you have to expand it all out with no parentheses anywhere, okay? And then you look at the highest power of x and you look at the number in front. Good question. Good question. All right? Some things we need to understand about n, all right? N must be greater than or equal to 0. All right? In order for us to call it a polynomial function, the highest power of x can't be negative, okay? If you get a negative power up here, it's no longer a polynomial. You're looking at something completely different that we don't talk about in this class, all right? So n has to be greater than 0, and n also has to be an integer. Do y'all know what the integers are? Like the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can't have a fraction up here. You can't have a fraction as a power. If you have like a fraction up there, like x to the 1/2, you're no longer looking at a polynomial function. All right? So that goes for every x you see. Every power you see up there must be some integer. So let me give you an example. If we did this function right here, that is not a polynomial function because this right here is okay, right? That's a positive counting number, right? 1, 2, 3, 4, 5. So that's okay. This right here really means x to the 1/2 power. That's what the square root means, and that's a fraction, and therefore this would not qualify as a polynomial. We're not going to talk about these at all right? But I just want to be clear on that's what it takes to be a polynomial, all right? So the next question, I guess, is what do these look like? You know, we know what linear functions look like. We know what parabolas or quadratic functions look like. But what do polynomials look like? And I have good news and I have bad news, all right, when it comes to this. The good news is I can tell you a little bit about what they should look like. All right, so I'm going to erase this. So what do they look like? Well, first of all, I can tell you this. If n is equal to 0 or n is equal to 1, it's a line. Give you an example. F of x equals 3x plus 1. And then let's look at this one. F of x equals 4. Okay, these are two examples. Well, is this a polynomial function?
Yes.
Yes, okay. What's the degree of this polynomial function? 1, right? So this is saying that if n is 1, then you're looking at a line. And we all know we could graph this, and this would be, that's supposed to be a line, okay? Like if we graph that, that would be a line, right? Now, this one right here, what's the degree? 0, because there is no x here, right? So the degree here is 0. I'm going to put here, n here is 1, here n is 0. And this is saying that if n is 1 or 0, then you're going to have a line. What would this line be? F of x equals 4. Straight line. Vertical or horizontal? Horizontal line. It would go through 4. It would go like this. This is the same as saying y equals 4. So this is a horizontal line, but it's still a straight line, okay? So in those two cases only, you have straight lines. Second thing I can tell you, if n is greater than or equal to 2, so that means this takes care of 0 and 1, right? But if n is 2, 3, 4, 5, 6, 7, 8, 9, 10, 100, a million, doesn't matter. As long as it's greater than or equal to 2, then the graph is curvy. Curvy, C-U-R-V-Y?
Yes.
Doesn't seem right. Curvy. All right? I'm going to show you some pictures of these, but you're guaranteed that if n is greater than or equal to 2, your graph is going to be curved. Now, think about it. When n is 2, we're looking at a quadratic function, aren't we? And do we all agree a quadratic function is curved? Yes? But if n is 3 or 4 or 5 or 6, we're also going to have curves, but there will be more. Yeah. Last thing I can tell you is this. The end behavior, this is the first time I've used this word, or these words. The end behavior is one of these. Okay, so let me try, I'm going to try and explain this visually. If you're looking at a polynomial function, what happens at the ends of the function, like out to the right and out to the left, those are the ends. The behavior of your function out at the ends is always going to be one of 4 things. Okay, so here's the first possibility. I'm going to draw just a quick picture. What we can have is that out here on the end, our left side can go up and our right side can go up. That's one possibility. Now I'm going to give this with an example, all right? For now, just take it for what it is, and it'll become more clear as I do some examples. We can have that, or we can have the left side go down and the right side can go up. What do you think the other 2 possibilities are?
Both going down?
Both go down. You could have the left side go down and right side go down. So you can have the left side go up, right side go up. You can have left side go down, right side go down. You could have left side go down, right side go up, or finally, left side up, right side down. Now the key to this is I'm using the word end behavior. This has nothing to do about what's happening inside the middle of the picture. This is only talking about at the edges. So this is saying that, look, when we go to draw a polynomial, when we go to sketch it, if it were this case, then as I draw it, whatever's happening here, as I start to draw it this way, I would eventually have to just keep going up forever. And as I draw it this way, it would have to just continue going up forever. Can you think of something you've already done that does that? Well, that was supposed to be red. Doesn't a parabola behave this way? Mm-hmm. Right? A parabola does this. On the left, it goes up forever. On the right, it goes up forever, right? And then if that parabola happens to be flipped over, it's like this, right? What behaved like this? What is an example of something that is a polynomial that would go down on the left and up on the right? How about a straight line? Don't straight lines do this? On the left side they go down forever and the right side they go up forever? Or the straight line could go like this. So no matter what your degree is, not no matter what your degree is, as long as you're looking at a polynomial, when you draw it, it's going to have to look like one of these 4 things, all right? So just let's back burner that for now, and I'm going to show you some of them, all right? So you can have an appreciation for what they look like. I'm going to have the computer graph them. And then maybe after you look at them, you'll understand how these are useful in the real world. We'll see. All right, so here's an example for us to look at. Okay, can you all see that all right? Can you all make sense out of that? This polynomial, I can't reach up there, but let's just imagine that's an arrow that goes up and an arrow that goes up. So this thing looks like this. Okay? This is a polynomial function. Which one is it? That one right there. See that? x to the fourth plus 4x cubed minus 37x squared minus 64x plus 336. Right? That's nasty. That's a nasty looking polynomial function. What's the degree of this polynomial?
4.
4. What's the leading coefficient? 1, right? Highest power is 4, leading coefficient is 1. This is what it looks like, all right? That is not a parabola. That is not a straight line, right? But it does have a characteristic that the left side does appear to be going up forever, right? And the right side appears to be going up forever. So the end behavior is this one. Do y'all see that? But there's a bunch of other stuff happening in the middle, right? It's curving, going back and forth. And it actually hits our x-axis a few times, doesn't it? Hits it here, 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 and here. Right? So we have x-intercepts. So our ultimate goal today is to be able, for me to hand you one of these and you sketch it. That's the goal, all right? So I want you to look at this. This is the polynomial function, and I've already factored it for us. So going from here to here, do y'all see that? Going from here to here is factoring. Now, do we know how to factor this? What methods have we learned? When we factor, the first thing we do is what? Greatest common factor. Here, we would not have one. We would not have a greatest common factor. Then what do? You count the terms. How many terms do you have?
5.
How do we factor 5 terms? We don't. In this class, we don't. Okay? We don't. So going from here to here is beyond the scope of this class. All right? So I will not ask you to do something like this. What I would do is I would actually give you this. I would give it to you factored already. And then from there, you'll have to sketch it. But what we're going to do, and right now I'm just trying to get you to see like what it looks like, all right? Do you notice where these x-intercepts are occurring? Can you tell? Let's see, 1, 2, 3. Here's 3. Here's 4. This one's at -4, and this one's at -7. Can you tell from this where those are coming from? Yeah? It's this factored form, right? Setting each of these equal to 0. If you set that to 0, you're going to get 4. That to 0, you're going to get 3. That to 0, you can get -4. That to 0, you can get -7. And that's going to give us our x-intercepts, right? Okay, so I'm going to change one thing on this graph, just one small little detail, and I want you to see what an impact it has. I'm going to change the function just slightly. What I'm going to do is I'm going to make this right here an x minus 4 squared. So I'm going to throw an additional x minus 4 into this. And I want you to look at the graph and see what happens. I think this is where I want to. I did that wrong. Hold on. Okay. So take a look at that. All I did was change this from an x minus 4 to an x minus 4 squared. How did that impact my polynomial function? What happened to the degree? It got higher. So now I'm a 5th degree polynomial, right? My leading coefficient's still 1. But take a look at this. Do we have the same x-intercepts? Yes. We have the same x-intercepts, right? But I want you to kind of focus your attention on what's happening here at 4. Okay, so maybe you can see it if you look at what's happening here at -7. If I were drawing this, would I cross through the x-axis here if I were drawing this with a pen? Would I cross through? I would, right? I would cross through there. It goes up. It's too far up there. It goes way up there and then comes back down, and I would cross through again, right? Come down. Would I cross through at 3? Just a little bit, right? Just a little bit. But what happens at 4? It just touches it. Do y'all see that? It's almost like a ball that bounces off and goes back up, right? The reason it bounces off at 4 is because I changed it to a squared. And you're going to see this because I'm going to write this all out and we're going to have notes to go and graph these, but I'm just trying to point these things out visually right now. If the factor in here is squared, you're going to bounce off. Let me square another one of these. How about if I square this one? all right? I'm going to square this one. And I want us to, well, you know what? I'm not going to mess with it. I'll do this one, 7. I'm going to square that one, all right? So I'm going to square it, and let's see what happens. What's going to happen to my degree? It's going to go up, right? But take a look at the graph. Okay, do we have the same x-intercepts? Yeah, same x-intercepts. But now, what does it look like? What does it look like the left side is doing this time? What does it look like the left is as we go that way? Like it goes up, right? And on this side, does it look like it goes up? So now we're back to this, right? At 4, because it was squared, it bounced off, right? And at -7, doesn't it bounce off this one now? Do you all see that?
Yeah.
Okay, so something about this power right here, and that power is a 1, that power is a 1, that power is 2. Something about that power dictates whether or not you bounce off or if you actually cross through. Do y'all kind of buy that right now? Okay. All right, do y'all want to look at any more of these? Let's do a 4th degree polynomial. Let's do it where let's see, 3rd. Oh, that's, yeah, 4th. Do this one plus 1. Yeah, let's just do that one right there. Let's take a look at this one. It's a 4th degree polynomial, right? 4th degree polynomial. Here I've already had the computer factor it for us. Because this is x minus 4 to the first power, I should expect that I'm going to just cross through at 4, right? Do I cross through at 4? Yes. Yeah, so here's 4, right? Notice I crossed through there. At 1, I should expect to cross through because this is a power of 1. So cross through, right? And at -3 would make that 0. At -3, I should expect to touch or bounce off. All right? And what about the end behavior? What is the left end of this function doing? Going up or down? Up. And the right end behavior? Up, right? Okay. All right, I think we're ready. All right, I think we're ready for me to give you the set of steps on how we're going to graph these. Oh, by the way, where in the real world do you think you would see things like polynomial functions? Yeah, I mean, pretty much anything that fluctuates, right? Anything that fluctuates. You're going to have stocks, stock market, anything that fluctuates, you can try and figure out if you can find a polynomial function to model what's going on. Yes, question?
So what determines the end behavior?
Yeah, good question. What determines it, right? So now I'm going to tell you how we are going to get all this. Right now I'm just trying to get you to see the things that, I didn't want to be like, let's give you the steps and you have no idea what we're talking about visually, all right? So now hopefully you have a little bit of an idea visually of what we're trying to do. Now let's go through the steps on how we're going to do it, all right? All right, so here are the steps. Sketching polynomials. How to sketch a polynomial. First step, make sure it's a polynomial. I'm just going to put poly, okay? Make sure you're looking at a polynomial. Which means that you have, a bunch of terms with x to different powers and all that, and the powers have to be positive counting numbers. You can't have any fractions, no negative numbers. Okay, once you do that, what we're going to do is we're going to find the degree and the leading coefficient, which you all have already shown me you can do. Okay, so we're going to identify the degree and leading coefficient. All right, that should be easy, right? Just look at it. We're done? Yes? Okay. Find the degree and the leading coefficient. The next step is to determine the end behavior. And that's what Luke was asking, right? Like, how do we determine the end behavior? And here's how you do it. Okay, what we're going to do is we're going to use a chart, a table that I'm about to tell you, that I'm about to show you. Here's the chart. I'll put it right here. And this chart, I would allow you to have on the test. All right, so just draw this almost like a little tic-tac-toe. What we're going to do here is we're going to have, I'm going to put LC here, positive, LC negative here, N even, and odd. Okay, try and just copy that down real quick. So we're making a little chart here. And the way this chart works is that we're going to look at our degree, right? And our leading coefficient, which is n, right? N is our degree. And what we're going to ask ourselves first is n even or odd? Okay? If n is even, we're going to work down this column. If n is odd, we will work down this column. So after we determine whether or not n is even or odd, then we ask ourselves, is the leading coefficient positive or negative? If it's positive, we'll use this. If it's negative, we'll use this. So these are our four possibilities. Remember I said it's four possibilities? Here they are. So what happens if n is even and the leading coefficient is positive? Here's what happens. The left side will go up, the right side will go up, and in the middle, I want you to put a question mark because we actually don't know what happens in the middle. It could squiggle around a couple of times, but you're guaranteed the left and right sides will go up. That's if your n is even and your leading coefficient is positive. Now, if n is even and the leading coefficient is negative, then it's going to be that flipped over. It's going to be down on the left, question mark, down on the right. Now, if n is odd and your leading coefficient is positive, you're going to go down on the left and up on the right. And if the degree is odd and leading coefficient is negative, it's that flipped over. Up on the left, down on the right. So once you have that, let's just practice. I'm going to come back to the notes. Let's just practice real quick. Let's say you had a polynomial function like this, and it had some other stuff behind it. And let me just give you a couple of more examples. Let me see. Okay, so this right here, what would be the end behavior of this one? So your degree is what? Your degree is
Positive.
degree. It is positive, but in the chart, what are we concerned about when it comes to degree? We're worried about is it even or odd, right? So this is our degree. This is n, and that's 3, and that's odd, right? Okay, odd number. And then we look at the leading coefficient here, LC, and that leading coefficient is negative, right? So odd degree, negative leading coefficient. Odd degree, negative leading coefficient. This thing is going to go up on the left, down on the right. So that's what this one would look like. Up on the left, question mark, down on the right. Make sense? Mm-hmm. How about this one? Degree is even. Leading coefficient is positive. So it's going to go up, up, up on both sides. Okay, what about this one? Even degree, negative leading coefficient, so down, down. This one?
But it's negative.
Trying to trick you here.
But they say we don't work with negative.
That's right. This is not a polynomial function. Okay? Negative power. You can't have that. All right? All right, does that make sense? Okay, so it's going to be relatively easy for us to look at a polynomial function and know the end behavior just by looking at it, right? Yes?
Why can't it be a negative?
Because I told you it can't be a negative. Because,
Just making sure, 'cause I know you said it can't be a fraction, but maybe I didn't.
no, yeah, I
get it
did.
where you- Yeah,
If you look back, I said for a polynomial, n had to be greater than or equal to 0.
that's right.
Okay, so that's the part that was saying it was positive. Yeah. I mean, this could be graphed. I mean, there is a graph that goes with this, but the problem is it's not something we do in here, all right? Those get very complicated, and you have to use other techniques to graph those. All right, we good? Okay, so the third step is for us to determine the end behavior using this little chart, all right? The next step is to figure out the x-intercepts. Find the x-intercepts of our function. Does that sound familiar? I mean, we did that with quadratics, right? We did that with lines even. X-intercepts have always helped us draw things. And if these things are going to be squiggling up and down, it would be nice to know where all those points are, right? So we find the x-intercepts. How do we do this? We set the function equal to 0, right? We set the function equal to 0. We don't plug 0 into the function, right? That's different. We're not plugging 0 in. We are setting it equal to 0. And then how are you going to solve that? It's just going to depend, right? You're going to have to solve this, all right? Which means you're probably going to have to do some factoring, unless it's one of those big ones where I'm going to have to give it to you factored already, all right? With me? Okay. So you find the x-intercepts. That's your fourth step. The fifth step is to determine the crossing or the, did y'all like the idea, remember when I was showing that to you? Where I said if the power was even, it was bouncing off or just touching. Do y'all like the bounce? Did bounce make sense? Yes? So we have to determine whether or not we cross or bounce at each x-intercept. Let me try and illustrate this, what we're saying with this step, okay? Let me try and illustrate this and why this step is so critically important. I'm going to do it off camera, but I'm going to do it on the side here. Let's say that we go through a problem. I give you some polynomial function, and you determine that the left side goes up and the right side goes down, okay? Let's say we know that already, right? And then let's also say that we know that the x-intercepts are here, here, and let's say here, okay? That's all we know right now. We've gone through steps 1, 2, 3, and 4. We have found the left and right hand behavior. We know where the x-intercepts are. And now I'm going to try and draw this, all right? This step is critical because of this. I know that it goes up on the left, right? So I know from this point it has to go up. Why can't it go back down? Why couldn't my graph go down first, then back up? Then I have more x-intercepts, right? So that's impossible for me to go down and back up. So I know that from the leftmost x-intercept, I have to go up. And then from the rightmost intercept, I have to go down, right? So I have to go down. So the only thing left to do is fill the middle in, right? So do you agree that this is one way I could do it? Yes? But that may not be what the function's doing. The function may actually be doing this. It may be coming here, it may be bouncing off, and then crossing through, right? It could be doing that. It could also cross through, bounce, and then go back down. You see, there's all these different possibilities of what could happen here in the middle. And the only way for us to know which of those it is step 5. Step 5 will determine what's happening at each x-intercept. So we're going to have to put all this information together and then use our brains to kind of draw it. It's going to be like connecting the dots back in grade school, but like more than that, right? It's going to be a little bit more involved here. All right, so how do we determine whether or not we cross or bounce? Here's how we do it. We look at the factors. Remember, this step of setting the function equal to 0, we were going to have to factor, right? I don't know how many factors we're going to have. Every problem is going to be different. If the number up here, if that number up there is odd, we will cross. If the number up here is even, we will bounce. I tried to show that to you in the picture a second ago, and hopefully you believed it. Did you believe it from my picture? You could tell or no? All right. Once we determine this, and trust me, if you're confused right now, just let's work through a few examples. And I think after we do a few, you'll catch on and things will be okay. All right? It's always hard in the beginning when we're trying to give you the steps and we are not actually doing a problem. So the 6th step is to sketch it. Okay? We're going to do a sketch. You got to put all the information you just learned together to draw a picture. I should also point out that you see these different pictures I have over here? You see this red one?
Okay.
I could also have bounced off, gone way up, and then maybe not as high up here, and just bounced off a little bit and been like really high and then really shallow. When you do these, when you draw these, we do not care how high or low these things go. Okay? Like, all I care about is that you know it bounced up and then came back and bounced up again. How high you go is going to be different for every person in the class. You're not going to be graded on that. If I wanted to know how high this went, you'd be in my Calculus 1 class. Okay? That's where we figure out how high it goes. But not here, all right? We just want to know the basic shape. All right. You ready to do an example? I think you are. You look thrilled, just thrilled out of your mind. All right, so we're going to start with a very, well, not very, but pretty basic example. F of x equals x to the 4th minus 5x cubed. Okay, how do I want to do this? I don't want that to happen. Hold on. Minus 14x squared. Where's my coffee? That's terrible. The instructions here are for us to sketch this. Okay, sketch this. All right, first step. Is it a polynomial? Mm-hmm. It is a polynomial, right? Okay, so it's a polynomial. Poly. Okay, step 2 is to identify the degree and the leading coefficient. So what is the degree of this? Hold on, I have my sticks. Y'all seem so excited already that you are going to volunteer this answer, but let's get everyone involved here. And Danny G. Danny? I don't think Danny's here. I don't think he's been here for a while. We'll put this stick way over here. Put him in the corner. Rastim, you're up. So I'm asking Rastim what the degree is and the leading coefficient.